Okay, so just to recall the concepts that we have discussed earlier, so we have discussed nonlinear optimization problems in unconstrained case. For example, x1 plus x2, x1 minus x2, minimize f of x plus 2x1 square plus 2x1 x2 plus x2 square. So there we did not have any restriction. X1 and x2 can be anything. Only thing that is we had to guess one uh, initial point, starting point. X naught should be given, and there was no constraints were given. Now, what will happen if we have a non-linear function? Because for linear case we have seen we can use simplex algorithm or we can use Karmarkar's algorithm to find out the solution. But if they are linear, then only then the simplex or Karmarkar's method will be applicable. Just like LPP. But if we have non-linear and this are also non-linear, linear or non-linear, maybe this can also, this constraint can be linear, can also be non-linear. Similarly, there are less than type constant can be there, greater than equal to type condition also be there. Okay, so all those cases that we have to, they come under the constraint optimization, non-linear constraint optimization. Okay, so for that we have to use some concepts of convex functions, concave functions, stationary points, maximum, minimum, saddle point, then gradient and Hessian gradient, and also there will be some called bordered Hessian gradient, the bordered Hessian matrix. Some we'll define eventually, and then we'll call that first order necessary conditions delta f of x greater equals to 0. Then Hessian, that is h of x, either this is a positive definite, positive semi-definite, negative definite, or negative semi-definite, or indefinite. Depending on that, we can decide maximum point or minimum point or saddle point, anything. So all these concepts we have to recall, and then we proceed further to discuss one more. That is the shortcut. I think during the midterm paper evaluation, I have seen many of have gone through the approach finding the eigenvalues, but that's a lengthy approach. I have already mentioned that we can find the principal minors. If we can find the principal minors to be greater equals strictly greater than 0, positive, then we call it a positive definite. And for positive definite matrix, we have convex function. For convex function, we have minimization. So similarly, if we have a negative definite matrix, so this would be the principal minor will be first one, this D1, that is this term. The first term will be a 1 term will be negative. After that, the minor of order 2 will be positive. And then it will be alternatively positive and negative for negative definite matrix. But for positive semi-definite, we will have this kind of situations. First one will be strictly greater than 0, positive, definite. Semi-definite will imply at least one of them is 0. Similarly, for negative definite, so D1 will be negative. After that, D2 greater equals to 0 and D3 less equals to 0. So these conditions are actually very useful to verify whether the function is given convex or concave. So if you look at this example, then we can find this. That is, this is a matrix. So this is a D1 is negative. So D2 is positive. And then D3 is once again negative. So it is negative, positive, negative. So it is negative definite. So whenever it is negative definite, this will imply this is concave, concave function. And concave function will lead us to maximization. Okay. Similarly, if we have this one, so these two examples are from our midterm. So if we remember, so yeah, this is just simple. Take the minors. No need to find out the uh, eigenvalues because it will take much time. So we can see that some these are not satisfying. So D1 is positive, D2 is positive, but D3 is negative. So this is indefinite. If this is a positive definite, then all should be positive. D1, D2, and D3 all should be positive. If it is negative definite, then it should be positive, negative, and positive. So it is not satisfying any of the criteria. So this is neither positive definite nor negative definite. So that is why it is neither convex nor concave. Now, if we are lucky, the function that we are going to minimize or maximize, this can be written as a sum of three functions or sum of some different functions which are actually separable. Okay. Now, if you remember the convex addition of convex functions f1x plus f2x, remember this is convex function plus convex function. This resultant is also convex function. So this approach can be applied, that we will take individually all the minimum points and then find out the minimum point for the given function. So the technique is same. We will try to find out the first order derivative, then find the second order derivatives. Similarly for all the variables. So each function is convex. So convex plus convex function plus convex function plus another convex function. The resultant will be convex function. So we will have a minimum point. And for finding the minimum point, we have to make them 0. And for from here, we'll get x1 equals to 6, x2 equals to 2, and then x3 equals to 3. Now, if you substitute these values on the given function, so here we can find this is our minimum, z minimum. The objective function value has the minimum value. But if we are not lucky, I mean, most of the time will not be lucky. This type of separation cannot be done every time. So these functions will not be able to do the separation. We cannot write it as a combination of f of f1 x1 plus f1 f2 x2 plus f3 x3. So this cannot be done. So we have to apply new techniques. And also it is not telling whether we have to maximize or minimize. It is telling determine relative maximum or minimum if following of the problem is applicable. Now the easy task is if it is convex, if convex, then we will get minimum. But if concave, then we will search for maximum. Okay, so for that we have to find out the first order derivatives and then second order derivatives and the Hessian matrix. We have to find out the Hessian. So this would be n by n matrix. So we have to find out the stationary point where the derivative is 0. So after making this equals to 0, so we can find out this is x2, and from here we can find x2 equals to x3 by 2, and then from here we can find x2 equals to 2x3 plus 2. So we equate them. These two equations are equated and then solved. After solving, we can find this is our stationary point. Okay, so x star is actually 1 by 2, 2 by 3, and 4 by 3. So this is our stationary point. Now, whether it is maximum or minimum point, that we have to decide with the help of Hessian matrix. So we calculate the Hessian matrix, and for that we need to compute the second order partial derivatives. So we compute all the second order partial derivatives. Okay, and then we substitute these values here. So we can see that the first element, if you think about the A11, that is the D1. The D1 is negative, and then D2 is actually positive, and then D3 is again negative. So that means the principal minor of order 1 is negative, principal minor of order 2 is positive, principal minor of order 3 is negative. So we are getting alternate positive and negative. So that is why the matrix, this Hessian matrix, is negative definite. Okay, so this is negative definite. All other are crossed. So this is negative definite. This is crossed. This is also crossed. Since this is negative definite, okay, so we can call it a concave. So that is why this is a maximization problem. Okay. And the maximum value will be this one. Just substitute this problem. Now, if you remember that optimization can be classified into two terms. Either it is unconstrained or it is constrained. Similarly, this constraint can also be separated into multivariable case and single variable case. Similarly, this is also bifurcated into this single variable case, multivariable case. Another bifurcation can also be there for single variable case. So this is a linear case and then non-linear case. Again, also this is linear case, non-linear case. So all of them can be linear, non-linear. But most of the times, if you constrain, this is unconstrained. When x can take value, this is the meaning of x1, x belongs to minus infinity to plus infinity. So this is an unconstrained problem. X. So this is a very trivial case. A straight line. Wherever you fix the point, that is their maximum point or minimum point. But if it is a square type or cube type problem greater than 1, so this becomes non-linear. So this class of problem are very trivial. Okay. But unconstrained linear and non-linear, unconstrained non-linear also, linear also not so interesting. You can see that here. For finding for particular this x value, this optimized will be this particular only. Yes. So this is not that much interesting, and difficulty is also not there. All three cases. Okay, the difficulty comes whenever we have unconstrained and non-linear case, and we have seen that how many there are several search techniques are there. Line search technique, then visible region technique, then Newton's method, then gradient descent approach, conjugate gradient descent approach, all those things we have seen here. Once again, if you go constant optimization problem, so whether this is linear or non-linear, that is not, actually these are very simple cases for single variable case. No need to discuss that much. In fact, from the childhood, we have discussed these problems. If f of x equals to some x square is given, or x, if we fix the region, x belongs to some range, x belongs to a to b, then we can find the maximum and minimum value in this interval. So that's one constraint. Okay, the difficulty will be, we have seen the difficulty arises when we have multivariable case. Even if it is linear case, then also it took several years to solve, from 1939 to 1947. There was a, so that was Danzig. Professor Danzig has proposed a simplex algorithm which gave effective solutions for linear problems. So these are actually, this is the class of LPP. Now we are going to discuss about constant multivariable linear problems. In fact, you will be realizing that we have seen some of the concept of this constant nonlinear optimization we have discussed in earlier one of the classes. So more or less, this is a nonlinear function. Nonlinear function will look like of this form over the nonlinear region. So this is kind of maximize or minimize fx subject to g of x less than equals to some b. So both are nonlinear. Okay, this is also nonlinear. This is also nonlinear. Okay. So if we have such kind of problem, then this is the constraint. Under this region, over this region, we have to find out the minimum point of this function or the maximum point of this function. Okay. Now some more examples. If we have this kind of function, then what will be the minimum point? So this is unconstrained. So in order to solve this constraint optimization problem, we will take the help of unconstrained optimizations. So that is why we have first defined and we have discussed the unconstrained optimization techniques. So the first and most simple and popular case is actually Lagrange's, or you can Lagrangean multipliers method. What is this method? We have to, if you remember, how we have found the dual of a given LPP. So if you remember, we have multiplied with A1 and then A2 and found an upper bound. So that means if you try to find out in this case, let me see, let me write down here again. So we had defined that 8x1 plus 6x2, that was defined by, I mean not defined by, it was bounded by the A1 plus 3A2 into x1, then plus A1 plus 2A2 into x2, which is also bounded by 5A1 plus 12A2. And we have found that this is going to be one upper bound. This is one upper bound for the objective function. Okay, as you can see, this is our objective function. And not only that, this is also upper bound. For A1 equals to 5, not 5, for A1 equals to 8. If you take A1 equals to 8, then we have seen that this right hand side it becomes 40. So 40 was one of the upper bound. And then we have seen if we add 3, A2 equals to 3, so this becomes 36, one of the upper bound. And we have seen that if we take the infimum, or the minimum, infimum of this set of infimum of collection of these upper bounds, then this will be equal to some W function. Okay. So that means if we try to, what we are doing is actually, if we try to define the function in this form, minus, so let us write it in this form. So what we are doing is actually, so let us write this is g1 x less equals to some 5, or let us write b1, and then this is g2x less than equals to b2. Okay, and this is fx. Let us write f of x, z equals to fx. So the multipliers, if we multiply with some lambda, for example lambda 1, and this is multiplied with lambda 2, then f of x minus g1 into x, not g1, lambda 1 into g1x plus lambda 2 into g2x. Okay, and if we take the infimum of this, okay, so this problem will be a minimization problem. For a linear case, whenever this fx and this one becomes equal, for this particular problem, we had seen that this is the optimum solution is f of x star is equals to 34. Okay, and if we find out the infimum of these points, so for example, this is 34. If we select lambda 1 equals to 2, lambda 1 and lambda 2 also 2, then this becomes 10. 5 into 2 is 10. Then 12 into 2, that is 24. So 24 plus 10 is 34. So this is also becoming this will also become 34. So that means the infimum will be 0. So fx minus this portion will be 0. Okay. Because linear functions are those functions which are both convex and concave. So that is why this gap, this is a primal objective, and this one will be the dual objective. So there is, at the optimum level, they become equal. But if it is non-linear function, then this gap may not be equal. This may not be 0. And that positive gap is called duality gap. In fact, this process is called dualization. Okay, so in order to define formally, how do we call it? And these lambda i's are called multipliers, Lagrange's multipliers. Lagrangian okay. So let us define formally for non-linear case. So for linear case, we have seen that we can, for a given any linear problem, we can find another linear problem, and now we can now we are telling that this is actually the Lagrangian dual. So this particular process is called a dualization. Dualization. So this method is also known as Lagrangian multipliers method. So we'll start with a simple case, because this is this function can be convex and concave also. And we are because of that we are having this one is as equality type. But if this is a maximization problem, it is natural to get this is a less than type constraint. If it is a minimization problem, then it is expected to have greater than type constraint. But we'll think about only the equality first time. After that, we'll define what will happen if we have inequalities. So we have a case. So instead of maximize or minimize, we can write optimize. And for Lagrange's multipliers method, what we need is actually we have to define h of x1 and x2, another function equals to 0. The right hand side will make it 0. So that, okay, the given function, the given constraint, we have to make it a 0. The right hand side becomes 0. So g1 x1 and then x2 minus b equals to 0. So there also, if you make it, if you take it there also, yeah. Okay. Let me show you one more difference. So if you take it here, lambda times x1 plus x2 minus 5 plus lambda 2 into 3x1 plus 2x2 minus 12. Okay. and if you are trying to find out the infimum. So this will be of the form is actually. So this is our g1 x1 x2. This would be our g1 x1 x2. So this is g2. Okay. In this case, it will be of this form. We are taking here only one function because we want to define only simple case first, and then we will go for difficult case. So both are non-linear functions. This can be non-linear. This can be linear also. No problem. Okay. Both can be non-linear. And then we have to define a new function, Lagrangean function. It is also known as augmented Lagrangian function. Now, what is the meaning of augmentation? To make someone's value large. For example, if you remember the system of linear equations, if we enter the B matrix here, right? And we call it an augmented matrix. That means we are increasing the size of the matrix. So that is augmented. So similarly, here also, the function was f of x1 plus x2. Now we are increasing the value, the size of the function, we are improving, we are increasing. Okay. So that can also be one explanation for calling such name augmented Lagrangian function. But most of the time, when there is no confusion, we do not use this augmented. We can directly use the Lagrangian function. So this is what we have only one constant h of x1 and x2, so lambda. Now we know the necessary condition for unconstrained optimization problems. So what we are doing here, see, this is our constraint, this is our objective function. We are taking this constraint to the objective function by some multiplying the multipliers lambda, and now this problem has become unconstrained. This is now an unconstrained optimization problem. So for this, what will be the necessary conditions? Del L of x equals to 0. So this is nothing but del L, del x1, del L, del x2, because the number of variables has increased for this L function. And then del L, del lambda. Okay. So this is our gradient now. So this is 0. So this becomes 0, and individually they will become 0. Okay. How about the second order? So if we differentiate, what will happen? because the function has now changed its shape. L is the LF and lambda into h of x1 x2 is there. So this is nothing but lambda times HL of. So this is okay. Note that lambda times h1 h of del x1 into. So if we just simplify, tail of f1 is nothing but lambda into del h del x1. Similarly for this one also, and here we get minus h equals to 0. So the necessary condition for optimum, we are not telling about maximum or minimum, we are telling about optimum. Okay, so these are the case. So this is 1, 2, and this is 3. Minus h equals to 0. Now, if the objective function is a concave or it is a convex, then these are not only necessary conditions, these will be sufficient also. We don't have to calculate the Hessian matrix now. Sufficient also if this is satisfied. Okay. Now let us see one example and then we'll try to look at other things. So for example, this is our f of x, this is our g of x equals to 2. So we have to make it h of x equals to g of x minus 2 equals to 0. The right hand side should be 0. Okay, then fx. And then we have to, so that means we have to x1 plus x2 minus 2 equals to 0. So lambda times the gx. Okay, and then fx is there. So this is nothing but fx minus lambda times h of x. Okay. Now if you try to find out the del L del x1, because we have only 3 variables, 3 unknowns, x1, x2 and lambda. These 3 are unknown. So for this we'll have, so this is 4 minus 2x1. Then here x1 is there, so minus lambda 1. This is del x2, del L del x2. This is 8x1, 8 minus x2. This is 8 minus 2x1, x2 minus again this is lambda. Sorry, lambda only. And then del L del x del lambda. What it will be? So lambda terms are not there, so only the lambda is only here. So negative of x1 plus x2 minus 2. At a stationary point, what we will make? We'll make them 0. If you make them 0, then we have 3 equations, 3 unknown. So we can find a unique solution. Okay, so let us make it and try to find out the solutions. So we can find here x1 equals to 0, x2 equals to 2 and lambda equals to 4. Now, if we try to find out the, in fact, this function we did not know whether this is a maximization or minimization. For example, if the function is optimized, okay, then we have to find out the, the second order partial derivatives also, if you try to find out. Okay. So this would be del L, del X. In fact, we cannot claim this is okay. So if we try to find out the Hessian matrix of this form, so it will not be useful. Why? Because L is the augmented Lagrangian function. It is not the original function. Okay. So that is why we need to do some more extra task. So what are those tasks? Let us observe. Okay. So when the concavity and the convexity is not known, for example, this is only optimized, then we can directly find out these lambda values are of this form. And then we try to find out this is delta n plus 1, which is a principal minor. It's a determinant of this functions. So this would be delta 2. Okay, so this one is, so there are first order, this is first order. The first row and the first column will have first order derivatives, and then we will have second order derivatives. Okay, so this is actually the name of this matrix, okay, is actually bordered Hessian matrix, that we will discuss sometime later. But this is for your information that we have to find out this quantity and this quantity and this quantity 3, because we have m equals to number of equations. Here it is 1, and n equals to number of variables. It is 2, x1 and x2. Okay. So this result says the necessary condition provides an optimal solution to the problem if the sufficient condition for determining whether the solution results of this maximization or the minimization of the objective function involve n minus 1 principal minors of the following determinant. So this is principal minor, this is 0, and if you go, this is n by n matrix. So we will have only n minus 1 principal minors. This is already 0, and this one is, after that, this is principal minor of order 2, principal minor of order 3. Okay, so that means we'll call it lambda 3, lambda 4, and lambda 5, etc. If they have alternative signs, positive, negative, then it is a maximum point. If it has a all negative, then it is a minimum. Okay, so this is a useful result which we will use now. So from here, fx is this one, and try to find out del fx, del x1, and the second order partial derivative, and then substitute here. So minus 2 minus 4 into 0, that one we have calculated. So this is just simple calculation. You can make it. Now we try to find out whether this is greater than 0 or not. If it is the determinant of the principal minors is 0 or not. So this matrix will be as, in fact, this is delta, let us call it delta 3. n equals to 2 and m equals to 1. So delta n plus 1. So this becomes delta 3. For delta 3 matrix, we can see that we have this is positive. Okay, so it is sufficient to verify only one principal minor, n minus 1. Remember, it says it is sufficient to verify all the n minus 1 principal minors because we have only two variables. So 2 minus 1 principal minor, it is sufficient to verify only one. And there's order of this principal minor is 3 by 3. Okay, since this is positive, so we can call it a maximization. Hence the maximum value will be calculated. So this was our maximization. In fact, when it is, if it is written as optimize, then do not confuse. It can also be written as optimize. So x1 is 0, 0 square, 8 into 2 is 16, and then 2 square is 4. Okay, so this is 12. So that's our exact solution. So these are the case if we have only one constraint. But if we have more than one constraint, then the function will look like of this form. Fx, and then g1 equals to b1, then g2 equals to b3. So this is a compact form. In fact, x lambda n. So here what we will have? We will have one. These are actually HR actually. This is, if you take it on the left side, make it 0, then it becomes h1. Take it, make it 0, it becomes h2. Take it on the left side, make it 0, it becomes hm. Okay. So we will actually have m different constraint functions, h1x, h2x, hmx, and we'll write it in the Lagrangean function. That means the constraint problem is transformed into unconstrained problem. Okay. So once it is becoming unconstrained, then we can apply our calculus approach. So for this function also, we will have the necessary conditions for this optimum. That means here it will be, how many functions are there now? X is x1, x2, xn. And this lambda will be lambda 1, lambda 2, lambda m. M different constants. So we have m plus n partial derivatives. M plus n. Now if we try to obtain the sufficient conditions, it is actually given by the ordered Hessian matrix. So this was mentioned during the lecture when we have discussed quasi-convex functions. Quasi-convex functions. So how do we get this function? Let us define. Okay, the order of this matrix is m plus n times m plus n. So 0 is an m by n null matrix, that is 0 matrix. And P is a matrix containing first order derivatives of the, in fact, you can call it a Jacobian of, because we know that Jacobian, it takes, in fact, Jacobian transpose. This would be, yeah, here it is. Jacobian transpose of H1, H2, dot, 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 Hm divided by, okay, derivative of, okay, anyway. So this is P, and if you take the inverse, so this would be P transpose, and then Q is a matrix containing the second order partial derivatives of the L function. Okay. So what we are doing earlier, if you remember, we had only, if we have only one constraint, so we have only one row, one column, and one row with first order partial derivatives. And after that, we have second order partial derivatives. So this is one kind of bordered Hessian matrix here. And then we will continue for this function. So this is, now if you try to look at the structure of this function, it will look like of this form. This is Hessian bordered matrix. Okay. In fact, it is a block matrix. So for block matrix, this is 0 matrix, m by n, m by m 0, and then this would be actually m plus n by m plus n. So there would be another, this function would be n by m, P transpose. P transpose is a matrix, is m by m. P is a matrix which is m by n. And this is Q matrix. This would be n by n. So this is how this matrix will look like. Okay. Now, once we make the necessary conditions to equal to 0, if we satisfy from here, we will find out the values of x star and lambda star. We'll find out. Okay. So after finding this, what we have to do? This is very important. We need to determine the signs of the last m n minus m. Remember, there we had n minus 1 because only one constraint was there. So now we have to verify n minus m principal minors of the bordered Hessian matrix. Okay. So starting from the principal minor of order 2m plus 1. 2m, m is the number of equation. Now this will maximize, the function will be a maximization function if the signs alternate. Okay. And if this is the same sign, x to the power m has the, all the signs are same, and x to the power m type, then we will have minimization. For bordered Hessian matrix, it is difficult to define the positive definite or negative definite directly, because for bordered Hessian matrix, it is containing first order derivatives also. But originally Hessian matrix is actually a collection of second order derivatives. Okay. But here we have to use first order and second order both cases. So that is why we use the concept of bordered Hessian matrix. Okay. So let us discuss one problem and solve and explain how this is actually going to work. Yeah. So this is our first condition. We make it h1 of x1 and x2 equals to x1 plus x2 minus plus 3x3 minus 2 equals to 0. h2, this is x1 x2, this is 5x1 plus 2x2 plus x3 minus 5 equals to 0. And this is fx equals to x1 square plus x2 square plus x3 square. Okay. So let us write f of x minus lambda 1 times h1x plus lambda 2 times h2x. Okay, so this is nothing but of this form. Now we try to find out the necessary conditions. We make the, so how many variables are there? Total 5 variables. X is or x1, x2 and x3. And lambda having 2 variables, lambda 1, lambda 2. So there are total 5 unknowns. So for that we have to find out these partial derivatives, find out, and from here you try to find out x1 equals to half of lambda 1 plus 5 lambda 2. From here x2 we get half of this lambda 1 plus 2 lambda 2. From here we get x3 equals to half of 3 lambda 1 minus plus lambda 2. So once we get this, we'll substitute this value in the next two equations. So what are those equations? We have to differentiate, partial differentiate L function with respect to lambda 1 and lambda 2. So we get these equations, lambda 4, sorry, equation number 4 and 5. Now we have found x1, x2 and x3, okay, from the previous three equations. Now if you substitute them, then what you will give? The first equation will be of this form after substitution, and then second equation is this one. So if you solve these two equations, because two variable, two equation, so it is solvable, and then we get lambda 1 and lambda 2 values. Now once we get this lambda 1 and lambda 2, if you go back and check from directly, if you substitute here, then you can find x1, x2 and x3. So this is x1, x2 and x3. So now we can we have these values. X star we have calculated is 0.804, 0.348, 0.283. So this is x star, and lambda star is this one. What is it? 0.087 and then 0.304. We have calculated these values. Then what we have to find? The bordered Hessian matrix, HP. What it will? This is 2 by 2 0 matrix, the block matrix, because 2 m equals to 2 here and n equals to 3 here. Okay. So n minus m, what is it? 3 minus 2. How many delta we have to find out only one. So only one principal minor is needed to verify. Okay. And if you just try to find out the second order derivatives, it will be okay. So try to verify. Okay. So the next task is to find out the determinant of the principal minor of order 5. So coincidentally, this is only 5 order. So 5 by 5 order. So this is delta 5. We have to find out. Okay. The principal minor. So let us evaluate this principal minor. The determinant of order 5 by 5. Hand calculation is very difficult, but it has so many zeros. So this will be some kind of helpful. Okay. So if you just use the traditional approach and proceed as follows, finally we can see that this is greater than 0. So what it implies is actually if this is a positive, so the function will be minimization and the minimum value will be of this type because it was x1 square plus x2 square plus x3 square. So this is our final optimal solution. Now the question will be, sir, how do we evaluate this kind of determinant of 5 order? Okay. So for this we need to find out computing tools. Help. You can use MATLAB, you can use Excel. There is no problem. But finding this matrix is important. That this is the way we find out the bordered Hessian matrix. Okay. So determinant, we can, if you put these values, substitute these values in some computing tool, so it will directly give you the uh, final value. So whether it is positive or negative, depending on that, you can decide. If suppose this value was negative, then we can call it a maximization problem. After this, any doubt?
Sir?
Yes. Mhm.
Sir, we have defined Lagrangean to be f minus summation lambda h.
Yes.
What if it is f plus summation lambda h, sir? I mean, will the sign of the lambda alone will change, or uh, will we encounter any other problem while proceeding, sir?
That's a very interesting question. Okay. In fact, some of the textbook I have seen, they are using plus notation.
Yes, sir. That's why, sir. Even
Okay.
I have a tendency to use plus lambda at sometimes, so that's why I wanted to ask.
Okay. I think I don't actually. It won't make any serious problem. I don't think it will make any serious problem.
Okay.
The reason I'm defining with negative because I wanted to define that the duality gap. For linear problem, there is no duality gap because the primal at the optimum level, the optimal value, objective function of the primal, and the optimal value of the dual are
Ah,
both equal.
yes, sir.
Okay, so that gap is actually zero. So
Yes,
for
sir.
linear problem, because it is the problem, linear functions are special functions which are both convex and concave.
Okay, yes.
Okay, but if you think about a convex convex function, then its dual will be a concave function.
Ah,
Okay, so there we may not have that. Uh, the gap should not be zero. Okay,
right,
sometimes
sir.
the gap is non-zero. So that particular gap is called duality gap. In fact,
Okay.
in order to explain this duality gap, it can take uh, another lecture, but we don't have that much time. So that is why I am just mentioning the duality gap. Regarding your question, that is, if we take this positive, then what will happen? In fact, we can try what will happen if we take this.
Maybe for the same example, if we use plus lambda, we can I think we can spot the difference if you need.
Will it make any distinction?
Sir, I think the sign of the lambda value alone might change because if you take one minus sign outside the summation, we'll arrive at what I'm asking. But anyway, I'll try it out, sir.
Yes, yes. Okay. In fact, I also need to think about it. So I will show you that there are some problems where we actually think about the duality gap. So this is one example taken from this book called, if we have a nonlinear function, okay, then we will have a term which is called a duality gap. But for linear problem, duality gap is zero. So here we are having duality gap is as positive duality gap. This gap is called duality gap. I
Okay,
mean,
sir.
okay. So there are a lot of mathematics behind this graph. Okay. So I'll recommend to, if you are interested more, I'll recommend one textbook. I think I have added this textbook in the file. Let me check whether I have mentioned or not. Oh no, I have not. Okay. So let me show that book actually. This is a book by Mokhtar Bajara, third edition. Yeah, this one. So
You have by any chance a soft copy of this for online study?
Yes, I have soft copies. I have this one. In fact, for our syllabus, it is not important. But if you are more interested, you can go through this. That's my intention to tell you. So, article section 6. It is 6 point 12 gigabytes. Example 6.2. Page number 264. Yeah, page number. '64. So I'll add this soft copy to this folder. Okay. And you can access this textbook also. Okay. So for your practice, I have added three simple problems and try to verify these problems. The first one is only one constraint, two variable. This is three variable, only one constraint. This is three variable and two constraint. Try to verify the results, whether they are correct or not. And then in the next class, we'll define if we have f of x minimize, f of x, or in fact maximum. If it is maximization, then we will have inequality. Okay. Subject to, for example, g of x less than or equals to b, or we can write it many variables, many constraints will be there. So far we have discussed only equality type. Okay. So if it is inequality is there, then we have to introduce the slack variables. Then how this Lagrangean method will be modified and the necessary and sufficient conditions will be converted into some other factors, that we have to discuss in the next class. And that is the study of Karush-Kuhn-Tucker conditions. So we'll try to look at main aspects of KKT conditions in the next class. But till then, you will try to verify these results. If you have any more doubt other than that, what will happen if we take that Lagrangian function as a positive? In fact, this textbook also considers this as a positive. But for this particular topic, what I am following is actually they are taking negative.
Okay, sir.
This negative is really related to the gap actually. So that is why I was mostly interested, but I have not thought about if we take the positive. We have
Okay,
to
sir.
check. We have to check whether these computations, for the example, these results, what will happen to these results. In fact, you can verify it right now. If you take this will be positive, right? Instead of negative, you are asking for positive. Let us write positive here. Positive. All will be positive. Then what will be happening? This is negative. This is also negative. This will be negative. So if you substitute here, this is negative. This is also negative, will be there. Then negative and negative. So the right hand side is negative. You can multiply with negative 1 again. So it becomes positive. So I don't think it will make any serious changes. Values, lambda 1 values and lambda 2 values will be same, I think. Though
Okay,
it
sir.
is a rough idea, okay, we have to verify carefully. So
Okay.
try this, try to verify this result. Okay. Try this with positive, okay, positive lambda 1 and lambda 2. Then you will find the difference. I think you will get the answer.
Okay, sir.